Good morning, one and all. My name is Endur Gaurav from AC Department, Vignan Snirila. Today we'll discuss the analysis of linear systems. That is introduction to the analysis of linear system. First we'll see the definition of a system. The system will be defined as a combination of a device or a one particular device which can be operates on a signals and produces another output signal. That means it will transform the input signal and produces the output signal like this. It will take the input as a particular signal and produces the output y of t. It will transform the input signal. Y of t will be nothing but it's the transformation of the input signal x of t. It's the transformation of the input signal x of t. That means it will take the input signal, it is excited with the input signal and produces the output signal. This output will also be called as the response of the system. Generally, we can take the more number of inputs like this, as we'll have a number of inputs here and produces a number of output signals also. That is, with the number of input signals, we can get the number of output signals. There is no restriction of the number of inputs and no restriction of number of outputs. That means system is a device which converts a particular input signal and produces the outputs. Next, the classifications of the systems. Generally, the systems will be classified into these categories, like first one as linear and non-linear, time variant and time invariant, linear time variant and linear time invariant systems, static and dynamic systems, causal and non-causal systems, invertible systems and non-invertible systems, and stable and unstable systems. These are the general systems what we'll have. Next one, the first will stay with the linear and non-linear systems. Basically, this linear and non-linear system would satisfy when it satisfies the superposition and homogeneity principles. Let first consider the signals, that is x1 of t and x2 of t, and produces the output y1 of t and y2 of t respectively. Then according to the superposition and the homogeneous principles, we'll get that is when the system will be multiplied with the a into x1 of t, that is called as an homogeneous system, like this, homogeneous system. Then the output also should be multiplied with the a, that is a homogeneous. Next, if we have a signal x1 of t, then the another signal x2 of t. For the x1 of t, the output is y1 of t, y1 of t. For the x2 of t, the output is y2 of t. If I take the sum of these two, that is x1 of t plus x2 of t, then it will be passed through the system and produces the output y1 of t plus y2 of t. Then it is called as a superposition system. If we multiply a constant a to the input and produces a constant a at the a into output, that is a homogeneous system. If we multiply x1 of t and produces y1 of t, x2 of t, y2 of t, sum of the two signals and produces the sum of the output signal, that is a superposition system. Therefore, that is called as the corresponding superposition. When we combine these two, then it is called as a linearity system. Linearity system. Linearity system. That is, when we take the input as a into x1 of t plus b into x2 of t and producing the output as a into y1 of t plus b into y2 of t, then it is called as our linearity system. That means when we take the transformation to the corresponding a into x1 of t plus b into x2 of t, then it is being given as a into y1 of t plus b into y2 of t, like that. That's called as the transformation of the weighted sum of the inputs and producing the weighted sum of the outputs. That's called as a linearity system. If the transformation of this particular weighted sum of the inputs is not equal to the weighted sum of the outputs, then it is system is called as the non-linearity. That means it does not satisfy this homogeneity and superposition principle. It does not satisfy the homogeneity and superposition principle. And the next type of classification is the time variant and time invariant. The system is said to be time variant if the input and output characteristics vary with respect to the time. If they vary with respect to the time, it's called as time variant systems. That is, the input and output characteristics varies with respect to the time. It's called as time variant system. And the time invariant system is said to be if the input and output characteristics does not vary with respect to the time. It's called as time invariant system. For calculating this particular time invariant and time variant, the condition for it is the y of n comma t is equal to y of n minus t. That is, the condition for the time variant system is y of n comma t not equal to the y of n minus t. If both of them is been equal, it's the time invariant system. If the both of them is not equal, then it is the time variant system, where this particular transformation of x of n minus t is the input change and y of n comma t is the output change. That is, the output change and the input change will be different. When we take the input change and producing the output is one thing, and changing the output itself is called as the another one. If both of them is been equal, then defaultly it is called as the time invariant. If the both of them is not equal, then it is called as the time variant systems. Next one has the linearity and the time invariant systems. Linear time invariant and the linear time variant systems. It's simply the when the system satisfies both linearity and time variant, it's called as linear time variant system. That's called as an LTV systems. If the system that satisfies linearity and time invariant, it's called as linear time invariant systems. If both of the systems has been satisfied, that is called as the time variant systems. If the both of the systems, that is linearity and time invariants, are satisfied, it is called as the linear time invariant systems. Basically, the linear time invariant systems are practically realizable, but the linear time variant systems are not practically realizable cases. Next one is the static and the dynamic systems. In the static and the dynamic systems, where these particular static systems is nothing but is the memoryless systems, whereas the dynamic systems is the memory systems. When the output requires a particular memory to store its values, it's called as a memory system, which is the dynamic system. Where it does not require any memory, it's called as a static system. That's y of t is equal to 2 into x of t, where for the calculating the present value at t is equal to 0, the system output is y of 0 is equal to 2 into x of 0, and the output is only dependent upon the present input. Therefore, the system is said to be a memoryless or the static. Similarly, next example, y of t is equal to 2 into x of t plus 3 into x of t minus 3. At the present value of calculation at t is equal to 0, the output depends upon the present value x of 0 and its past value x of minus 3. Where it depends upon the past value, therefore we need to store that particular past value. Hence, the system is said to be called as a dynamic system. That is, when it depends upon the dynamic past values, it is called as a dynamic system. When it does not depend upon the past values, where it depends only upon the present values, it's called as a static system. Next one is the causal and non-causal systems. In the causal and non-causal system, a system is said to be causal if the output depends upon the present and past values of the input. Present and past values, but it does not depend upon the future values. Whenever it depends upon the future values, it is called as a non-causal system. That is, which depends upon a non-causal system is the output depends upon the future values also. That is, along with the present and past and future values, then the system is non-causal. If it depends upon only on the present and past values, it's called as a causal system. If we take an example, that's y of t is equal to 2 into x of t plus 3 into x of t minus 3. For calculating the present value of t is equal to 1, the system, the output will depends upon the present value x of 1 and the past value x of minus 2. Therefore, the output depends upon the present and past inputs, and the system is said to be called as the causal system. Similarly, in the next example, that is when calculating the present value at t is equal to 1. Therefore, for calculating the y of 1, the output depends upon the present input x of 1 and the past input x of minus 2 and is the future input x of 4. Therefore, it depends upon the present, past and the future values. Therefore, the system is said to be called as a non-causal system. On a whole, that is when it depends upon the present and past values of the input, it's called as a causal system. When it does not depend upon the present, past, when it depends upon the present, past and future values, it's called as a non-causal system. That is the classification of the causal and non-causal systems. Next one is invertible and non-invertible systems. In the invertible and non-invertible system, the system is said to be invertible if the input of the system appears at the output. That is, input and output should be the same one. That is, the invertible system can be analyzed by using the Laplace transform like this. That's y of s is equal to x of s into h1 of s and the h2 of s, where the h2 of s will be the inverse of the first transformation, that is 1 by h1 of s. Therefore, h1 of s and h1 of s gets cancelled. Therefore, y1 of s is equal to y of s. That's y of t is equal to x of t. That is the same. The output and the input will be the same. That's y of t is our output, x of t is our input. When the output and the input are been same, then it is been called as an invertible system. When the output and the input are not being same, that's when if the y of t not equal to the x of t, then the system is said to be called as a non-invertible systems. Next one, the stable and unstable systems. In the stable and unstable system, a system is said to be stable when the output is bounded for the bounded input. When the output is said to be bounded for the particular bounded input. That means the condition is BIBO. Bounded input, bounded output. For the signal, if we have a bounded input, the output is also bounded, then the system is said to be, it's called as a stable system. Bounded signal means the amplitude should be the finite. The amplitude should be finite. Always should be a finite. It never should be go to the infinity. Always, for all the values of the t, the amplitude should be the finite. If it goes to the infinity, then it is called as an unbounded input. For example, y of t is equal to x2 of t. Let that input is an u of t step signal. Therefore, our y of t is equal to u2 of t, that is u of t bounded output. The output is the amplitude of u of t is always 1 for t greater than or equal to 0 and 0 for t less than 0. It will be continuously 1 only, it's finite amplitude only for the infinite time. From 0 to infinity, its amplitude is 1 only. That's why the finite amplitude, therefore this was a bounded input and output is the same signal, that is a bounded output. Bounded input, unbounded output. Therefore, the system is said to be called as a stable system. Similarly, for illustration of the corresponding unbounded system is, for example, if you take the y of t is equal to integral of x of t, and the same thing, take the integral of u of t. When we integrate this particular u of t, that's integral of 1 dt, then we'll get the t. That t is continuously increasing. It will be, t is nothing but a ramp signal, it's continuously increases. At t is equal to infinity, its value is infinity. Here it is a finite, but at t is equal to infinity, it is being infinity. That is nothing but an unbounded signal. Unbounded signal. Therefore, the system is said to be called as unstable system. That is called as an unstable system. This is the classifications of the stable and the unstable systems.